Hello, my name is Dylan. I am a graduate student at the University of Nevada, Reno. I work in a synthetic chemistry lab that focuses on synthesizing small molecules to be used in anti-HIV research. Our lead molecule is a molecule called cyclotriazodisulfonamide, or just CADA for short. And this has been shown to effectively down-modulate CD4 on the surface of various immune cells. So a lot of research being done right now in the field of HIV treatment is focused on synthesizing molecules that could potentially inhibit various stages of the HIV life cycle. Our molecule down-modulates CD4 expression on the surface of T cells. CD4 is the primary receptor that HIV uses to enter and infect the T cell. So this makes CADA a potential entry inhibitor for HIV. So a typical day working in the lab in Reno as a chemist would consist of running various reactions, working those reactions up into a form that you could purify and isolate your desired compound. And then taking that purified product and analyzing it through various spectroscopic methods that allow you to determine, if you have what you think or hope you have. Once you confirm that you have your desired molecule, you can use that molecule in further reactions all the way up until you get to your target molecule. For me, that typically consists of usually 5 reactions. But anywhere up to 10 or 12 reactions to get to your final product, often starting from something very, very simple and building your way up to very, very complex molecules. So I have several different research projects going on right now. My main focus is on figuring out which amino acids on the signal peptide are involved in binding to CADA. This is done through a technique called photoaffinity labeling, in which you introduce essentially you synthesize an analog that has a photoreactive group on it, and then you allow that to bind to your target. You shine UV light on it, and it generates a very reactive intermediate that will quickly insert into whatever's nearby. So the idea is that if it's sitting in the binding pocket, it will just covalently bind to your target. Then you can go back afterwards and figure out, which amino acid it's bound to, and that should hopefully give you a better idea of how the molecule is interacting with its target. We're interested in this because we would like to, figure out which amino acids are important, and then, design more potent analogs based on those amino acids. Additionally, I'm also working on some permeability studies. I'm currently at KU Leuven here. I'm growing some cells that can be used to model the monolayer of cells in your GI tract. And then you can essentially look at how a drug would move between your GI tract into your bloodstream and vice versa, to figure out, how well is this drug going to be absorbed if you take it orally? Are there transporters on cells that are going to be necessary to move this drug across into the bloodstream? Does it get absorbed at all? Essentially it's just figuring out what's going to happen if you were to take this drug. So I've been in the lab for just over a year now, and I really enjoy the work I do. It is cool to know that you could be producing or helping produce something that could help a lot of people. But it's also very cool to see the collaboration between our lab, which is synthetic chemistry, and then the molecular biology side here in Leuven, and really seeing the different expertises come together and produce something that's worthwhile. I think that's really really important in actually making scientific progress. So yeah, I'm excited to see what happens in the next few years. And I hope that this has given you a little insight into what working as a researcher in a medicinal chemistry lab is like. So.